solving quadratic equations. Now, I always hear, doesn't matter where I go, how I do it, that math is always hard. Math is always difficult. Okay? Math always, I don't understand it. I don't see where to go. I don't understand what to do. And one of the things that you've got to understand is that these things follow a pattern. Okay? When you're asked to solve a quadratic equation, all you're doing is looking for a value that has a certain quality to it. Either it makes it equal, makes it greater than, makes it less than. And the graphing calculator is a great picture for this, which is why we use it quite a bit. That's why graphing and actually having a visual display of what's going on with it is extremely helpful. Now, if I take a look at this here, and of course there is the one other thing that students definitely do not like to do, and that's read. Those four-letter words that students are trying to avoid. So, U.S. Energy Information Administration expected retail prices for a regular grade automotive gasoline to average $3.15 in 2011, 37 cents per gallon higher than the 2010 average, and $3.30 per gallon in 2012, with prices forecast to average about 5 cents per gallon higher in each year during the peak driving season, September. Now it says the real price of a gallon of gasoline adjusted for inflation from 1990 and projected to 2012 can be described by the function. Now, when you're going through and reading that, there's a lot of stuff there. It's confusing. Well, what do they mean? What are they talking about? Simplify. Okay? Just telling you that they expect it to be, gas prices are going up, tells you what the prices are for that, and they give us a formula. When they give us that formula, what should we do? Got a formula, pop it into the graphing calculator. That's generally your first. That's generally the first thing that you want to do. Let's go. So, second plus 712, we reset. Y is equal to. It resets. There it goes. So, I put the information in there. I've got point. That there. 0.006x squared minus 0.054x plus 1.78. Okay. Now, did I do anything spectacularly difficult? No. I popped it into the graphing calculator just to see what I was going to get. Have I done anything else yet to it? Well, we've got x. What does x represent? Is it talking about, is x gas prices? Is x time? Is x something else? Almost always, in problems like this, our domain, our x variables, our input, is always going to be some sort of time. So in this case, we're talking about gas prices per year. So does that mean that we've got gas prices per year coming in? Yeah. Our time is in years. Now, they say that this thing is projected from 1990 to 2012. We've talked about this before, and I know some of you have been having difficulty running that one through your head again. Okay? Anything that is from that point is just from 1990. That's it. Okay? 1990 is your starting point. It's your zero, where we begin. Now, as I keep reading, it says where X is the number of years after 1990. So it just told you what X was. The price of the gasoline has a large impact on consumer spending, so viewing and understanding the pattern indicated by this model can help consumers make decisions about taking actions to reduce gasoline use, such as switching to alternative fuel vehicles, using public transportation, or reducing commuting time. Although, except for one of those, it'd be almost impossible to do that up in this neck of the woods, right? To find the year in which gas prices are expected to reach $5 a gallon, we solve the quadratic equation. Now, there are different ways of doing this. I'm going to take a look at the window here before I go on. Do I care about negative 10? And the answer would be no. Why? Because we're starting off at 1990. We're worried about 1990 going forward. We're not worried about 10 years in the past. So that's zero. We're going from 1990 to 2012. Let's see, you know what? I'm going to go down here and I'm going to give this thing 30 years. Okay? This 20 years puts us out to 2012. 30 years would move it out far enough so we got things to see, step by one. Now again, I'm leaving the y at negative 10 like I've done in the past. That way I can see what's going on with the x-axis. I was hoping what's the highest gas price should go? I don't want $10 gas, but with $10, is it possible theoretically? Yeah, could be. So my 10 right there, I'm just going to leave it and just see what happens when I graph this. Okay, so I graph this out. Do I get enough resolution off the graph? Okay. Well, gee whiz, I got the negative 10 sitting there in the middle. It'd be kind of nice to see more definition to this, so if I want, go back here, and I'm going to drop this down to, say, negative 2, because I still want to be able to see where the y-axis is at. Ditch that. And let's see, you know what? Negative 2, thank you. And I think I'm going to put 8 in here. So now I hit graph. Now I've got a nice graph. Actually, prices look like it went down there for a while and started going back up. Now, there are a couple of ways to go through and figure out when this is equal to 5. Now, if you take a look at what they did down here, is they went and said it was equal to 5, and they moved the 5 over, and they went and changed the y-intercept, which is fine. We will be having to use that quite often, especially if we're going for numerical answers. But what I like to do when I am using something like this is I will go back here, y, and I will put in what value I want it to hit. I want it to hit 5. So I'm going to put a line here at 5. So when I hit graph, you end up seeing a line going across. So, do they intersect? Do you know how to find the intersection of two graphs? Oh yeah. So we go second, calculate, and we hit 5, intersect. That's one graph, that's two graph. Yes, no, you will figure it out yourself. So it says 28, basically in 28 years from 1990, we should be looking at $5 a gallon gas according to this formula. So that would be what year? Basically 2 years from now, right? So according to this model, what should it be now in 2016. Well, how many years is 2016 away from 1990? 26 years. So if I go and press my trace and I go 26 and I put it in there, we should be paying $4.42 or 43 cents per gallon, right? Or about half that. Better than that, right? Now, of course, this formula was simply based upon observational data from a period of, a few years. Is that accurate? According at that time when this thing was created, that wasn't an accurate function. So a lot of this really comes down to putting the function in, seeing what it's equal to, where it's at. Now, I said mathematically that we were going to end up having to do it a little bit differently. So, what we need to do is go through and we have to deal with our factoring. Okay? Now, I'm going to show you a couple of ways of dealing with this. Generally speaking, that if you are told that you have to go and factor something mathematically, especially on an ACT test, and they want to see your work, you actually have to go through the work to show the work. But 9 times out of 10, they're looking for the solutions, and I'm going to show you how to deal with this. As soon as this decides to come up here. So, here we go, finished. So, we've taken a look at how we go through and factor these things. Now, first thing that I'm going to do here is I'm going to bring the 6 over. So I'm looking at 3x squared plus 7x minus 6 is equal to 0. We always go through and set things equal to 0. Okay? Now, I can't factor that 3 out of the 7. That just isn't going to happen. So, I got to take a look at the 3 and the 6. When I multiply those together, I get 18. So I want to take a look at the factors of 18. So 1 and 18. Let's see, 2 and 9. 3 and 6. And that should be it, correct? Those are all the factors. Next thing. When I factor this out, what are the signs going to be? Well, if this is negative, one of these has to be positive, one of these has to be negative. This is not correct, according to that chart that I gave you a few days ago. Now, because the signs are different, I need to find the difference in a pair of factors that would get me to a 7. Is there a pair of factors that if I take the difference, I get to 7? This is the tricky part, guys. What's the difference between 1 and 18? 17. Is that 7? What's the difference between 3 and 6? Well, the difference between 3 and 6 is 3. Is that 7? No. What is the difference between 2 and 9? 7. So that means I have now got to work with the factors of 2 and work with the factors of 9. Well, the factors of 2 are 1 and 2. That's it. 1 and 9. 3 and 3. Now, somehow, some way, I need to get to a negative 6 here. Okay? Will multiplying 1 and 9 actually do that? Is there any way I can use 9 to get me to a 6 when I multiply? The answer is no. Is there any way that I can use a 1 and a 2 and a 3 and a 3 to get to a 6? And the answer is yes. Now, The catch is here, when we multiply the outside and then the insides, these are what give us our difference in our middle terms, yes? One of them has to be a 9, the other one has to be a 2. Well, and if I look at this, the 9 must be positive, correct? So that's going to have me put 3 here and 3x over here. That forces me to go and put the 1x over here and the 2 over here. How do I know this? Okay. I know this because 1x times 3x is 3x squared. 1x times negative 2 is negative 2x. 3 times 3x is plus 9x. When I add these together, I get a positive 7x. 3 times negative 2 is negative 6. So I factored this. I have yet to solve it. Okay? I've only got it factored. When we've got this thing factored out, we are concerning ourselves now with x plus 3 and 3x minus 2 is equal to 0. When we are looking for solutions to this, there are going to be two solutions. Now, the only way for something to be equal to 0, for those of you that are awake, is if x plus 3 is equal to 0 or 3x minus 2 is equal to 0. This is part of the reason why we go and set it equal to 0, because there are some wonderful little things when we're multiplying by 0 that we know about. Specifically, something times 0 has to be equal to 0. So, solve. Subtract 3, x is equal to negative 3. Add 2, 3x is equal to 2, divide by 3, x is equal to 2/3. These are what are called the solutions to this problem. Okay? Now, this is a boatload of mental gymnastics. The only way that you get good at these things is practice, and then guess what? More practice. Now, are there some ways to help guide you with this? Oh, most definitely. Because it's always kind of handy knowing what the answers are, right? So I'm going to go back up to the top here, and we're going to use the trick that I had just showed you up over here. So my equation here, what I am going to do is I am going to take what's on this side and put it on one line, and I'm going to take this and put it on the other line. I'll show you how that works. So clear that out, and I take 3x squared plus 7x. Then I go down here and I put in 6. Now I'm going to reset my window to negative 10, 10, 10, and 10. This is why it would have been easier to reset the calculator button. I hit graph. There comes my parabola. And there comes the line. So now, we had said that this was going to come through where? We said one was at negative 3. If I go and hit my trace and I go and put in negative 3, what does it say it's equal to? 6. Isn't that what we wanted? Now the other one that we've got is 2 divided by 3. So I hit trace again and I put in 2 divide 3. Yes, you can put in a fraction. I press enter. What does it equal again? 6. Is this what we wanted? So this is a way of visually going and checking your answers. Now, we had also changed this thing over so that it was equal to 0. So if I hit y equals, and I'm going to go down here and I'm going to put another one in here, and I'm going to call it 3x squared. There you go. 3x squared, let's see, plus 7x minus 6. And I am going to hit graph now. Okay. So now it's going to throw in another parabola for me. So this is where it's supposed to be equal to 0. Do we know how to find zeros with the graphing calculator? Sure we do. We hit second, calc, and I want to find number 2. I want to find a 0. Now, on my calculator, it comes up, I've got things color-coded here a little bit easier for you to see. But what was the last equation I put in? That was y sub 3, right? So I want to arrow key down. I'm at y2, arrow key down again. So I'm at y sub 3 is identified here, and I want to find the 0. Now it says the left bound. Well, that's on the left side of it. Am I on the left side of that one? Yep. So I'm going to press enter, and now I want to find the right side of it. So now I'm over here, enter, and I don't want to guess. I want you to do it. It says 0.66667. Is that not 2/3? If I want the other one, we get that again, second calc, and we do the 0, and left bound. So now I got to move over here. Sometimes it's easier to cheat on an easier one. So I'll cheat on that one. Oops, I cheat on this one. There we go. So I'm on the left bound. I'm definitely left up. Enter. And let's see, right. So now I'm on the right side. Enter. Somewhere between those two lines, it tells me it's at -3. So you've got different ways of going through and doing this. If you're supposed to go and factor, you have to go through and factor it out. Now, the nice thing about this is, once I know that those are the actual factors, I can check it here, or I can reverse it and say that, hey, it's got to be equal to these things. Okay? It is really just a whole boatload of taking your time and going through and figuring out where things are at. Okay? Height of a ball. We've talked about these before. It says the height above the ground of a ball thrown upward at 64 feet per second from the top of an 80-foot building is modeled by that. The equation. Okay? How long will the ball be in the air? Okay? So, reset. Step 1. Do I actually want to try and go and factor this thing out? No. Graph it. So, y is equal to negative 16x squared plus 64x plus 80. Is that my equation? Window. What is x talking about here? Okay. X is basically our t variable, and our t variable is the number of seconds, so that's time. Do I care what happened 10 seconds ago? Absolutely not. 0. Is a ball in the air 10 seconds probably more than sufficient to do the job? Probably. Now, y minimum. I'm going to leave the negative 10 in there again just so that I've got the definition. That's all I leave it there for. Y max. How tall is the building? 80 feet. If you throw the ball, is the ball going to go higher than 80 feet? So if I put in 150, would that be a reasonable amount? Yes? No? Maybe so? Graph. And a lot of times your first graph is your guess as to where things go. I got kind of lucky on that. Do I see enough of the graph to actually answer some questions? Yes. Now, it says the height above the... They want to know how long the ball was in the air. Now, you got to remember, this graph is a representation of the height of the ball based upon time. This is not the path that the ball takes. This spot over here does not represent that it was that many units far away. Okay? That represents how much time it took to hit the ground, because the height would be at 0. So if I look at it this, would it be reasonable to assume that it takes 1, 2, 3, 4, 5 seconds to hit? Okay. So let's just check that out. We'll go and hit the trace. We'll put it, well, look at that. It came up originally. 5 is equal to 0. So how many seconds did it take to hit the ground? 5 seconds. Again, most of this stuff is going to be putting in the information to a graphing calculator to see what you get. Now, we could have easily solved this thing just by factoring things out. You'll notice that it factored out here and gave me a 5 and a -1. Do I care that the ball could have been on the ground 1 second before I threw it? Absolutely not, because that doesn't make any sense. That means you would have had to have thrown the ball through the building. That ain't gonna happen. In the building. Now, I was talking about all these problems here, and they go to the graphing part. I honestly want you to be doing the graphing part of it as much as you can. Of course, if they tell you factor, then you had darn well better factor it out and have it written down. The reason that I kind of push the graphing part of this more so than the factoring part, in real live data, factoring things out to nice, easy numbers is almost never going to happen. Okay? So, you need to be able to put it in the graphing calculator and interpret what goes on. So, again, make sure that you read through the section into the beige box and see what's all there. And I don't think that I want to go through anything else for you. I will touch on this idea of the spreadsheet. The spreadsheet's a nice little thing, but it takes a lot more. You just can't slam it in there and go. A spreadsheet would be more useful, say, for like when you're doing your models, and because then you've got a lot more data that you are working with, as opposed to the graphic calculator where you're just putting the information in and going. So, now, one thing that I am going to go over here with you is this idea of the square root method. It's okay. They want us to use the square root method to go and solve these. Simply put, what that looks like is this. If I've got 2x squared minus 16 is equal to 0, we add 16, add 16. 2x squared is going to be equal to 16, divide by 2, divide by 2. X squared is going to be equal to 8. That means that x is going to be equal to plus or minus, because we're saying that something square is equal to 8. Now, this stuff that was up here that I slammed down first, all basic stuff. You guys know that should come out just as fast as I was doing it. So now, 8. Question, is there a factor that's a perfect square in 8? Think of the factors of 8. You got 1 and 8, 2 and 4 is 4 perfect square. Okay, if you find something that is the perfect square, why did you do that? So, we know that 8 breaks up into 4 times 2, correct? What's the square root of? What's the square root of 4? So this will be plus or minus 2 square root 2. That's all it is. Why? Square root of 4 goes to 2. Can't do anything with 2, so it stays in the square root, plus and minus. Let's try that over here. So, now I have got x minus 6 squared is equal to 18. Well, before I could do anything with it, I got to take the square root of that. So I get x minus 6 is equal to plus or minus 18. Does 18 have a factor that's a perfect square? And that should be what? 9. So we know that this is going to be 9 times 2. What's the square root of 9? 3. Square root 2. Now, in this instance, I've got x minus over here. I am going to have to create two problems because I have to add 6 to both sides. Okay? So that means that x is either going to be equal to 6 plus 3 square root of 2, or x is going to be equal to 6 minus 3 square root of 2. Because we've got the plus and minus here, we have to make sure that we put both of them in. But again, this is nothing new. You've seen this idea before. You take the square root of one side, then it has to be plus and minus. So, let's see. Anything else of interest? Yes. All right. The next thing. Talking about completing the square. Now, if there is one thing that is troublesome for students, it's usually this. Because this takes a whole boatload of mental gymnastics. I am not kidding. So, I want to solve this by completing the square. So just think you said it's. So, what we've got, we are going to go and take x squared minus 12x plus 7 is equal to 0. Subtract 7 to both sides. So what we see is x squared minus 12x is equal to negative 7. Now, when I write this down, I'm going to leave it with a little space like this. I'm going to show you why. First thing that we've got to do is we have got to identify which one of these is b. Now remember, we're dealing with ax squared plus bx plus c is equal to 0. This is what we start off with. What we need to do is find out what 1/2 of b is. Okay? So step 1, I want 1/2 of b. Okay? That's what I want to identify. So what value is b here? So what is half of that? Yep, negative 6. Then what we want to do is square it and add it to both sides. So what is negative 6 squared? Well, I add 36 here, and I add 36 over here. Now, remember when we're dealing with something that's an equation, we're talking about equality. Okay? And when we're talking about equality, what we do to one side, we must do to the other side. Now, as I continue on through this, what we're going to end up seeing is this factors out as follows. X minus 6 squared is equal to, and this turns out to be 29. Okay. How did I get to that point? Well, remember, x minus 6 squared means that I am taking x minus 6, multiplying it by x minus 6. Okay? Now, FOIL it out in your head. What is x times x? Well, that's x squared. What is x times negative 6? Negative 6x. What's negative 6 times x? Negative 6x. When I add them together, do I get negative 12x? Okay? What is negative 6 times negative 6? 36. So now we use that idea that we had for dealing with, come on, catch up, for dealing with squares. What we're going to do then is we are going to have to square root both sides. So now I've got x minus 6 is equal to, is there anything that is a factor of 29 that's a perfect square? And the answer is no, 29 is a prime number. So what we end up with is just saying plus or minus the square root of 29. What's the last step? Well, add 6 to both sides, add 6, and we end up with x is equal to 6 plus or minus the square root of 29. Now, unless you actually have some numbers that can be added or subtracted, you can get by writing things like that. 6 plus or minus square root of 29. Those are the values that go through and, solve this for where it's equal to 0. Now, if you were to actually have gone through and tried to, boy, this thing is slow today. If you would have gone through this and actually tried to graph this and see where it equals to 0, you would get some really strange looking numbers. Okay? So if I were to go through and do that, let's see where we go. Got that there. Calculator on. Give it time to show up. Second. Is equal to, let's clear that out of there. And so we'll go x squared minus 12x plus 7. And tell it to graph. Oops. There's some reset this. Terrible. Window. Negative 10. Okay. So, graph comes back up again, and I see this here. Now, mind you, I'm only worried about where it actually hits. Now, I've got one over here. I don't see the other one, do I? So, by the way, what would be the square root of 29? If you had to ballpark it, 29 is close to 25, right? Square root of 25 is 5. One above that is 6. So I would probably have to go and change my window here. So my x max, I'm going to move it out to 20 just to make sure that it actually shows up. So if I hit graph again, I see it come down. And I see it go back up. Trace. What is 6 plus second square root of 29? You can put that into the graphing calculator, and I can hit enter, and it goes and tells me that it is some wonky number, 1 times 10 to the negative 11th. The calculator has a wee bit of a problem with this, simply because it's putting a weird, irrational number in, and it has to approximate. When you see something like this, notice how it's flashing at 0. So guess what we assume that to be? 0. I mean, think about it. If you've got a decimal point, then 10 zeros, and then a 1, is that a really small number? So, again, this is also going to be part of the issue when it comes to dealing with spreadsheet. You're going to have to see. So, these are basics of it. Now, of course, there is one thing that always works. Quadratic formula. Become one with this. Make sure that you put this into your notes. Remember, you're pulling the A, the B, and the C out from the equation. Plug those numbers in and do. You've played with the quadratic formula before, so I mean, it's nothing spectacular. And actually, I think what we're going to do probably on Monday, make sure you remind me, is we're going to go over a procedure for putting this into a spreadsheet so make life a little bit easier for you to calculate. So, with that being said, I am going to let you get to work.